Hi, and welcome to Lesson 2.4. Today we're going to be doing a little bit of work with summary statistics, looking at what happens when you change a data set by a given number, things like that. The summary stats that you use to describe a distribution really depend on the shape of that distribution. If you'll recall, we said earlier in class that if a distribution appears to be normal, or mound-shaped and symmetric is another way to say that. Mound-shaped and symmetric. Then the mean and standard deviation are the best choice for center and spread. If a distribution is skewed, then the median and the IQR are often a better choice. But you know what? You'll never know that unless you graph the distribution to start with. So today we're going to focus on which measures of center and spread should be used for a given data set. We can't know that without graphing. To give just a little example of why it's important to use the right measures of center and spread. Think about this. How could we determine the total amount of property tax that say, Clio community, Thetford Township, can expect to collect if they know the number of houses, the mean value, and the tax rate? Well, if you know the mean, then you should be able to multiply mean times number of houses, and that'll give you a total tax base, right? That'll tell you the total amount of dollars there, and then multiply that whole thing by the tax rate. Knowing the mean allows you to figure out and to plan ahead for what's coming. It's often true, though, that when you're talking about the income of a community's resident, then the number they give is the median. Why do you suppose that might be? Well, you know the mean is sensitive to outliers, right? The median is not. So the median kind of ignores the highs and lows. So if you have one or two super rich people living in your neighborhood, they would drag the mean up, but they don't affect the median so much. The median, it's not sensitive to outliers or to extreme values. All right, let's talk just a little bit about the effects of changing units in a data set. And we're going to use this data set, which has record low temps. These are record lows, folks, for several world capitals. We're to make a dot plot. The lowest it's ever been in Addis Ababa is 32. So, folks, that puts them, there's 30, puts them maybe right around in there. In Algiers, it's also 32. So they've never been below freezing. Bangkok in Thailand, folks, the lowest it's ever been there is 50. In Madrid, 14. That's still pretty temperate. In Nairobi, never gone below 41, so a little bit more than halfway there. Brasilia, 32. There's another spot that doesn't get below freezing. And finally, we come to Warsaw, Poland. The lowest temperature ever recorded there was negative 22, so down in here. And you can see that that's a giant spread in temps. Take a second. We're going to convert each temperature to the number of degrees above or below freezing, okay? And we're in degrees Fahrenheit, so we want to subtract 32 from each temperature. Here you can see I brought my calculator up. I'm going to subtract 32 from each temperature. So you can do that in the list. This is really just a handy machine. So in list 2, I'm going to go up on the title and tell it to take list 1, whatever's in there, and subtract 32 from it. As you can see, the things that were 32 turned into zeros. So we have a 0, a 0. We have an 18, a negative 18, a 9, a 0, and and woof, a negative 54. My goodness. Hey, ladies and gentlemen, I bet you that you are noticing the same thing I am. That is, we may have changed the scale on this x-axis, but we surely did not change the shape of that distribution. So when you subtract or add the same value from every number in a data set, that will change the center. Folks, if we did the mean of these temperatures, it would be different than what it was before. But the shape and spread are not affected at all. And that's something important to remember. Suppose that we wanted to convert now each of those temperatures that we had into Celsius. We already have subtracted the 32, and the rest of this is dividing the difference from freezing, which we already have, by 1.8. You could also multiply by 1 over 1.8, but I'm going to go into my list 3, and I'm going to tell it to take whatever's in 2 and divide by 1.8. So we're dividing each value in a data set by the same number. We still have the zeros here, so we have 0, 0, 10, negative 10, 5, 0, and negative 30. Hey, I'm noticing something there as well. We still have the basic shape. The spread, though, is smaller. Instead of going from what we had before, 18 to negative 54, now we're only going from 10 to negative 30. So the spread has shrunk a little bit. You notice that the center is the same here, but that's because multiplying by 0 results in 0. So if we had a data distribution that was not centered at 0, that also would have changed a little bit. In general, folks, recentering a data set, that is adding or subtracting a constant. Adding or subtracting a constant of C to all the values doesn't change the shape or spread, but it does slide the center, hence the name recentering. Okay? Rescaling a data set, that is multiplying or dividing by some positive constant. That doesn't change the basic shape, okay? But it stretches or shrinks the distribution, multiplying the center and the spread by a factor of D. We divided by 1.8, and that made us shrink. If you think about the multiplying of it, multiplying by a fraction will shrink the data set, and that's kind of what we did. All right, let's go on. And we next want to talk a little bit about the influence of outliers, and we're just very briefly, we've already talked about outliers. The mean is considered to be sensitive. That is, it is affected greatly by extreme values, sensitive to outliers. The median is usually resistant. Percentiles and cumulative relative frequency plots. Well, folks, this is like a mishmash of some topics that they wanted to get in, and this is the last one here. We've used the term quartiles. The first quartile is called the 25th percentile. That is, 25% of values in a data set are lower than it. Or are beneath it. The median is the 50th percentile, since half the data in a data set is underneath it. Half data is below it. You can define other percentiles the very same way. In general, a value is considered to be at the kth percentile if k% of values, or data values, are at or below if k% of the data values are at or below it. I'd just like you to imagine for just a second a situation where you'd want to be at the 99th percentile. That is, you want your value to be at or above 99% of everyone else in the world. I'm sure many things will come to you, but some that I've heard over the years are wealth, IQ, happiness. It'd be nice, wouldn't it, to be happier than 99% of the world? If we were, so this is a look at it from the other perspective, what would it mean for us to be at the 3rd percentile of personal debt? Well, that would be good news for me, because that would mean only 3% of the population owes less than you do. And that would put you at a very low debt threshold. Only 3% of the population owes less than you do. That would be a good thing. We are going to end our lesson today by looking at a type of graph that can show cumulative percentages, like percentiles. This is called an ogive, which is a weird word. What they want us to do is estimate, it says, the quartiles and median. Our job is to create a box plot that shows this distribution, and the claim is that you can get it from this ogive, which shows cumulative percentages as you go through this graph. You and I both know that to create the box plot we need to have the 5-number summary. So the minimum, the quartiles, the median, and the maximum. The minimum value here is 250. So at the lowest percentile, 250. So there's our min. The 25th percentile would get us the first quartile around 440. I'd like to have you pause the video, please, and go after the median, Q3, and max. Here's my 5-number summary, and I'm sure yours is close to that. We're going to stop or pause. We're going to finish out this letter by drawing the box plot that's associated with. So I'll go ahead and draw it, and you can draw it as well. Let's see. If we go from 200 perhaps to 900. 3, 4, 5, 6, 7, 8, 9. All right, whisker at 250. Well, you know the drill. And there's our box plot. Very good. We'll ask you to get out there, do the U-try at your earliest convenience, and we'll see you in school.